Okay, ladies and gentlemen. Well, AP Chem students, I'm happy to start a new unit, as I'm sure you are. So our next unit is acids and bases. Okay, so make sure you take a look at the calendar. Today we're just going to intro some of this stuff, but ultimately we kind of have to start with the video lecture because we're going to fit our test corrections in on Friday and that sort of thing. So in order to kind of keep the calendar going and maintain some review days before the AP test, we kind of need to sneak this video lecture in, and hopefully it's just a review for you guys, and we'll go on from there. Okay, so today we'll get into more net ionic equation writing and stuff like that as we go. So I'm just going to kind of ignore the bell work for right now for this, and just kind of get into kind of some review stuff, and we'll calculate pHs and things like that. So it should be hopefully something we just dust the rust off of and we feel pretty good about, and that sort of thing. Okay, so an acid. What is an acid? Well, it's acidic in taste, which ultimately means that it tastes sour, right? Sour Patch Kids, lemons, things like that are acidic when taste. And acids, really, the deal is how can you identify an acid? Well, usually they always have an H in front of their formula. Okay, so that's a typical thing, and ultimately they're going to put hydrogen ions into solution, so they're donators. Okay, these guys are going to be donates, and they're going to make H pluses in solution. So when we look at Brown-Lowry, so we could write this two different ways, like HCl, you guys know hydrochloric acid, we could write this as H plus and Cl minus in solution, right? And we could also write it as HCl plus water, okay, formulating that's liquid water, so we wouldn't include that. And then equilibrium expression, H3O plus, H3O plus and Cl minus in solution. So the hydronium ion, that's that guy. You might see that every once in a while, hydronium ion. And the proton here, you treat these the same way, okay? That's the proton. You treat them the same way. Okay, when we're going to calculate pH and things like that, we're looking at ultimately we want to treat these guys exactly the same way. So you're looking for concentration of those guys in solution to calculate pH and things like that. Okay, so a base, remember, is bitter in taste. Okay, so they're slippery. They'll feel slippery on your skin and stuff. Chocolate, like really dark chocolate, cocoa, is that things that are high in cocoa, because cocoa is a base, that would be bitter. That's where the bitterness is coming from that we're talking about there for a base. Most cleaners are basic and things like that. And really the deal is these guys are going to accept H pluses in solution in water. So an example of, although in most cases you might be familiar with a base creating OH minuses in solution. And that's what they do, right? That's what they do by accepting, so weak bases. So the extraordinarily famous weak base, ammonia, NH3, okay, if we put that in some water, okay, that is going to accept an H from water to make the ammonium ion, NH4 plus, and hydroxide ions in solution. So something that you're familiar with, like when we put sodium hydroxide, you know that's basic. And as a result, it makes OH, because it's a strong base, it makes OH minuses in solution. Well, weak bases do the same thing. And ultimately, they are doing that by accepting a proton from water, H plus. Okay, so remember, there is a difference between strong and weak acids and bases. This is really important to remember this, all right, that we memorize the strong acids and strong bases. Okay, so this is going to be very important to us later. We need to be able to just look at a solution and its formulas and know whether or not we have strong acids and strong bases, or a weak and strong interaction and things like that. Okay, and just as a reminder, just because an acid or base is deemed weak yeah, they're still bad news. Okay, so hydrofluoric acid, for example, they're talking about like, you know, it can be real damaging on your skin. Well, hydrofluoric acid is actually used on glass to make that fogged glass. Okay, it can etch glass. So strong stuff. All right. So just as a reminder, the 7 strong acids. Hopefully, you can remember them as HCl, HBr, HI. Then we've got nitric acid, HNO3, and oops, our 2 chloric, our 2 perchloric and chloric acids, HClO3 and HClO4. And then our last one, which is also a diprotic one, which is sulfuric acid. Okay, it's diprotic because it can put up multiple H's into solution. And remember, the strong bases are all the group 1 hydroxides. Are all group 1 hydroxides and Zerbaca hydroxides. All right, all other hydroxides are weak, are considered weak. Okay, and so those are the strong ones. So if we flip the page, we want to practice identifying strong acids or weak acids, strong bases or weak bases. So really, if it's not on the list, it's weak. And then we just have to figure out whether or not we're looking at an acid or a base. So for example, H2S, our very first one there, okay? It has a hydrogen out front, all right? It is, and it is not one of our 7 strong acids. So this is a weak acid, okay? NH3, not one of our strong acids, no. One of our strong bases, no. All right, so amines, okay, amines, all right, these nitrogen with hydrogen on them, they are not charged. They don't have a charge, like a plus charge. That equals weak base all the way, okay? If they have a charge, they have a plus charge, that equals weak acid, okay? And we'll talk a little bit more about why that's the case, but ultimately you just have to be able to look at these compounds that contain nitrogen in them, and hey, all right, identify whether or not they're going to be a weak base or a weak acid. If they don't have a charge, like this guy, this would be a weak base. However, if they do have a positive charge, like the guy down below here, NH4+, that's going to act as a weak acid. Okay, right next to that, we have nitrogen plus these 3 groups on it. Well, right there, that's showing us that that is going to be an acceptor, so that it will be a weak base because it is not charged. You have a charge plus charge on it. You have a proton ready to give away. So that means this guy will be a weak acid. Okay, for those amine groups. Here's another one, an amine group. Oh, it doesn't have a positive charge, so this guy will act as a weak base. Okay. So you can go through and find those weak and strong guys, and you'll notice, like, hey, sodium hydroxide. Oh, group 1 hydroxide, that's a strong base. Here we have acetic acid. We have an H up front, so that's telling us it's an acid. One of our 7 strong ones, it is not. So it's weak acid. H4, and one of our 7 strong. Yes, it is. So that's a strong acid. HClO, oh, it doesn't have enough oxygen there to be strong, so that is a weak acid. All right. Magnesium hydroxide, is that a group 1 hydroxide? No, it's not, and it's not part of Zerbaca, so that is a weak base. All right. Down below, H2CO3, not one of our 7 strong, so that is a weak acid. PO43 minus. Oh, this is an interesting one. This is actually a weak base, and we'll talk more about why that is later. That's a conjugate base of an acid. Okay, well, we'll get to more of that later. Barium hydroxide here. Okay, that guy is one of our strong bases, so it's a strong base. HF is a weak acid, and it's also a high school in the southern suburbs, home of Flossmoor. Okay, HCl is a strong acid, we know. And this guy here is a conjugate base. So this is a weak base. And we'll talk more about that a little bit later when we do net ionic equations and stuff like that. All right, so kind of moving on. There are some molecules that can both act as an acid or a base. And the prime example of an amphoteric substance is water. Okay, it can gain, right? It can be a acceptor of an H plus, or it could be a donor of H plus and qualify for both a Bronsted-Lowry acid or a base. It can do both. Okay, so just keep in mind here. Remember the pH scale is that down below here. Runs from 0 to 14. Hopefully this is totally a review, right? Anything under 7 is acidic. If it's equal to 7, it's neutral. If it's above 7, it's basic. Keep in mind that it does go beyond 0 and it does go beyond 14. However, most things do fall within that parameter. But if you happen to get a negative pH, that's possible. For a number that's pH larger than 14, that is possible. Okay, so basically what it boils down to is acids have a pH that is less than 7. Bases have a pH that's greater than 7. Okay, strongest acids have pH closest to 0. Strongest bases have a pH that's closest to 14. Okay, and neutral substances are 7. All right, so log-based stuff. Here's a little more definition in terms of what it means to be log-based, but ultimately what we need to be able to do is we're going to have to get a little practice with doing some mental math with pH calculations and that sort of thing. So you'll get the hang of this a little bit as we go, but also here over on the side, we also have a mental math one calculator, a mental math thing here too, which I'll make another video and kind of walk through some of these and how to do these as well. It'll help us on that section of the AP test when we're not allowed to use our calculator during the multiple choice section. Okay. But for now, we'll be using our calculator and we'll just go on. All right, so for sig figs for pH, the whole deal for sig figs for pH is it's all about the numbers after the decimal are the ones that are significant. So we don't include the number in front. So if we're looking for 3 sig figs for our pH, you have to write it down like 7.123, okay? Those are the 3 sig figs, the ones after the decimal point, okay? So if we look at the first question there, how many sig figs does pH of 3.4 have? Well, there's 2 because it's the 2 after the decimal. All right, 4.0 has 1. 0.7000 has 4. So it's all about the number of decimals past the pH. So past the decimal point. So when we're doing, or when you're asked to give a pH, make sure that you give it. You should have 3 decimals. Okay, so review of calculating pH, pOH. Here are your formulas. And something that's really nice about these formulas is that actually all of these formulas here, all of these formulas listed that I'm highlighting right here are all listed on your yellow sheet. Okay, so that's really nice to have. Okay, now the ones that will be helpful to you are these 2 right here as well. Okay, and you just have to remember that we can go back and forth between pH, the fine concentration of protons or hydrogen ions or hydrogen ions, pH, 10 and raising it to the negative pH, or 10 and raising it to the negative pOH. So it's really that simple. But the nice part is you don't have to necessarily memorize all the ones that are highlighted there. They're given to you back to your yellow periodic table. But you'll use them enough that you'll probably end up knowing them anyway. Okay. So ultimately, we just want to use the equations above to answer the question. So if we have a hydrogen ion concentration of 1 times 10 to the minus 3, we can plug that into our pH equals minus a log concentration of H, and we'll end up getting 3. Okay. So it's kind of that simple in terms of when it's 1 times 10 to some number, right? And we're just going to the pH because we just bring that number because pH is basically a base time sort of deal. So it's very easy to just bring those points down. And that's what we get. Now, when we start putting some numbers out there, it's going to be a little different. All right, but ultimately, you know, in order to solve for the next ones here, we want to do pH. We're given the POH, right? pH is equal to pH plus POH, right, equals 14. Well, if we know that it's 2.65 is equal to 14, right, and we need to solve for pH, it's very simple, just 14 minus 2.5, and we end up with 11.5, right? And if the pH is 11.35, it's greater than 7, so that is basic. POH is 7, well, 14 minus 7 is 7. That guy is going to be neutral. All right, if the pH is 10.5, we know that that is a basic solution, and we know the POH is going to be 14 minus that, so 3.47. Okay, and these next ones here, the way I like to work these is I usually go for pH and then go for POH and kind of work my way around that way, rather than using the high, KW, and we'll talk a little bit more about that later. But the hydrogen ions times hydroxide ions equals 1 times 10 minus 14. I kind of avoid that one because it involves the some extra scientific notation, and the likelihood that we mess that up on our calculator kind of increases. So for number 8, what I would do is I would go minus the log of 1.2 times 10 to the minus 4, and I get a pH of 3.92. And notice there are 2 sig figs here, there are 2 sig figs here, right? And then I'm going to take 14 minus that number to get 10.08, right? And then I can take that and take 10 and raise that to the negative 10.08 to give me 8.3 times 10 to the minus 11, okay? So that's kind of the easiest way to go. So for OH, I can solve for the POH if I go minus the log of 3.4, second E minus 8. So I get a POH of 7.47. And if I do 14 minus that number, I get 6.53. And then I can take 10 to the negative 6.53, and I get 2.9 times 10 to the minus 7. All right. So, and then here, if I want to calculate the pH of a solution, notice this is a strong acid situation. So I need to have pH, right, which means I need to ultimately have the concentration of H plus in solution, right? So if I have 0.005 grams of HCl, 0.005 grams of HCl, I'm going to multiply that by 1 mole, all right, and there are 36.46 grams of HCl for every 1 mole of HCl. So ultimately we get 1.37 times 10 to the minus 4 moles of HCl. Because that's a strong acid, that means it completely dissociates in solution. So that means I also have that's going to break up into both ions. So I have 1.37 moles, or 1.37 times 10 to the minus 4 moles of H plus ions in solution, right? And I need concentration, right? So if I divide that by 0.120 liters, that's going to give me the concentration of H plus then. And that is equal to 0.00114 molar. So then all I need to do is to find the pH. That's equal to minus the log of 0.00114 molar. And pH is equal to 0.94. There we go. Okay. Then on the flip side here, we have some just practice problems. All right. So basically, same sort of thing, just giving concentration of H plus or OH minus, and you solve for the other and identify whether they're acidic, basic, etc. Okay. So I'll do kind of one example of each one. All right. So for A here, let's solve for the pH first. So that's equal to minus the log of 1 times 10 to the minus 5. Right? So 1 times 10 to the minus 5, if we take minus the log of that guy, that's going to be 5. Right? So that means the pH is equal to 9. Right? All right, and that means the concentration of H plus is equal to 10 raised to the negative pH, right? It's going to be 1 times 10 to the minus 9 molar. All right, and that gets basic. There we go. All that checks out right there. There we go. For exercise 2, you want you to calculate pH and POH for each of the following. So we have A, that is 1 times 10 to the minus 3 molar hydroxide ion. So POH is equal to the log of 1 times 10 to the minus 3. That's going to be equal to 3. That means pH is equal to 14 minus 3, which is 11. And that's all they were looking for. I don't have to do the concentration of H plus. Okay. And we can just keep on here. So they tell us pH of human blood is 7.41. Okay, pH, PaOH, all that sort of stuff. So concentration of H plus in this case is equal to 10 to the negative 7.41. Right? 10 to the negative 7.41, and that's equal to 3.89 times 10 to the minus 8 molar. All right, and I actually need to probably round that to 3.9 times 10 to the minus 8, because then that is 2 sig figs, because that pH gives us 2 sig figs, so we want to our answer on 2 sig figs, but if you give me 3, it's okay. POH is equal to 14 minus 7.41, which is 6.9, and then the concentration of hydroxide is going to be equal to 10 to the negative 6.59, 10 to the negative 6.59. So we end up with 2.57 times 10 to the minus 7 molar. Here we go. All right, so there we go. Pretty straightforward again. Once again, the next question, these guys are both strong, right? Both strong. So ultimately, right, this is also saying 10 H molar H plus is in solution. All right, and this one here is saying that H is going to break up into 1 times 10 to the minus 10 molar H plus ions as well as Cl minus ions, but we don't care about those because they don't determine the pH. Okay, and then finally here, same sort of deal. If this is a strong base, so it's going to break up 5.0 times 10 to the minus 2 molar hydroxide ions. Okay, so pH. So ultimately, we solve for POH, right, which is equal to minus the log of 5 times 10 to the minus 2. Which is 1.30. And we do for pH, it's equal to 14 minus 1.30, and we get 12.7. So there we go. If you got some questions, please let me know. We'll be using these formulas for the rest of the unit and stuff, so we want to get them down. All right, I'll talk to you guys tomorrow.